Could you then argue that the roof was done because of the fire? Not possible? No? Something fell on it, tore it?
I could tell him, I was like, okay, I'll just buy the couch and you can rip it yourself. Like,
In a panic, we, I don't know, drop something.
That's right. Okay. So we're going to talk today about the glue that glues the network and the data link layer together. So right now we've talked a little bit about the data link layer uses hard-coded fixed addresses to move frames around, and the network layer uses addresses to move packets around, and that inside of the local network, we only use the data link layer, and inside of the routers, we use the IP. But that really doesn't actually explain from an implementation point of view how all this actually works. So when a computer boots up and is completely unaware of itself, and we're not talking about anything that's been statically assigned, how do we get an IP address? Magic, right? So let's just think about this. When the computer boots up, the network card has no address assigned to it, right? It has no IP address. So then it needs to find an IP address from the DHCP server. How do you go about doing that? It has zero idea. We're going to broadcast. Correct. We're going to broadcast on what layer? What does our packet look like?
Data link layer?
Yes, we're going to broadcast on the data link layer. Technically, we're going to also do it on the IP layer, though it wouldn't get past a router anyway. But so, let's just put this, the data is DHCP request. So if this is our data, what's our next layer?
Network layer.
It's the network layer. And inside the network layer, we have a bunch of stuff, right? But we some of the things that we're really worried about in here is we have a source address and a destination address, right? Well, we don't have a source address, nor do we have a destination address, because we don't know what we are, right? So we need to figure out how to do that. And then we have a data link layer. And the data link layer has, among other things, a source address and a destination address. Do we have a destination address?
Everyone.
Huh?
Everyone.
We're going to do everyone. Everyone in Ethernet is 6 quads of everything, F's. So our destination is broadcast to Ethernet, right? What's our source address? Do we know that? Yes, we do actually know that. It's the only thing we actually know, because it is hard-coded at the manufacturer, right? So a network card knows its own address. So let's just call this 1.2. Or 1:2.3:4:5:6. What's our source address for the network layer? What's the IP addresses for the network layer?
Zeros?
Technically, I don't know if it really matters, right? Because DHCP is going to send it back at the data link layer anyway, but we can just, we can say zeros. If you look in Wireshark, you'll see all sorts of weird numbers in there. Like, I believe Windows puts out like 169 unroutable addresses. Right, what's our destination address? What's our destination address?
Everyone?
It's everyone. Two 555.255.255.255. Our destination is everyone. All right. So this goes out on the network, right? And it is a local request, right? So it goes out and is pushed through the network on the data link layer. The data link layer is broadcast, right? So it goes to everyone. Now, also recognize that this can only be one logical link away. So a logical link means that if this were a contested network, I would contest with you. Now, modern networks are switched, so it might be 15 switches deep, and that doesn't matter, right? Those are still the same logical link. And it goes to everyone. It goes to everyone because this is how the switch functions work when we built those tables, right? We broadcast. It goes out to everyone. And so now we have this host, and we have the DHCP server. And it will arrive at the DHCP server because of this. And the DHCP server will look at the contents of all the packets that arrive at broadcast and see, hey, is this a DHCP request? And it'll just say, hey, it is. What does the DHCP server send back?
Its location.
Oh, yes, right? So DHCP, so this is out. DHCP sends back what? Well, the source will be the DHCP address. Right? Destination will be what? This is the data link layer. Does the DHCP does it need to broadcast?
1.2.3.4.
It is. It's 1.2.3.4 in this example anyway. Right? So this will be routed directly and only to, at least on a switch network, it will arrive only at the destination computer. What is our source address here? Well, that's the source address of the DHCP server. So let's say that that's 192.168.0.1, which is common for a local home network. And then our destination address is what?
I'm going to go on a whim and I'm going to say a IP that the DHCP user or DHCP would recommend.
So possibly. It could be broadcast or the IP recommendation, right? It really doesn't matter because we're still routing on the data link layer, right? So the data link layer, no device inside of the data link layer looks at the IP until it gets to the host, right? So for the local network, all this stuff inside of here, right, is just data. The data link layer has zero idea what that is. It doesn't look at it. So it will arrive at the host, and because it has the correct source or destination address, the host will process it as an incoming packet. And there's some transport information here we probably need to talk about eventually. But and so it will process that packet, right? So it really, from an implementation standpoint, it could really be anything, right? We'd have to standardize it, and I'm not sure what the standard is, but it doesn't, like, from an implementation, doesn't matter, right? So let's just say that this is the offered lease. Offered lease of 200. So that goes back, right? Now what do we do? Do we have to do anything?
We have to request it.
We do have to request it. So this was the offer, this is the discover, and then we have to request. So that might be that, hey, you offered this address, I am going to take that. Right, the request. And so, and at that time, all of our IP information is filled out, right? All of our network address is filled out. We've discovered all of that, right? And then the server is going to actually have to acknowledge the lease at the end. And then you have a lease, which expires in some amount of time as set up by the DHCP server. What do we do at the end of that lease?
Relinquish.
Or renew. Usually, if a computer is on and up and running, it tries to renew. Right? It sets a timer as set by the DHCP server, and before the timer expires, the computer will renew. And the renew would only take 2 packets, so long as it was approved. All right. So this is how we get an IP address. And that functions just how it is, right? Because we're all on the same data link layer. We've also been doing this thing where we go down the network stack in a host, right? And then we come to a router, we go up the network stack, or up the stack a ways, and then rebuild the stack back down because we're on a different data link layer, different physical layer, and we go on. The question is here is, when you rebuild these data link layers, how on earth do you do that? So remember, on a local network, nothing is routed by IP. So you're on this, you have a switched network, right? And this host wants to talk to this destination, and it does so by IP, except for the local network does not understand IP. Ethernet does not, unless you have a layer 3 switch. Your home Ethernet, let's just put it like that, doesn't understand IP. So when you say, hey, I want to print at 192.168.0.200, because that's my printer, how does that work? Your local network doesn't understand IP. So what do we do? You're going to print. Yeah, it's going to be ARP. The question is, so that's address resolution protocol, but from an implementation standpoint, because we're actually trying to understand how this works, not just what it is, how do you make it work? How do you make it work?
Lookup table with the IPs and the MAC addresses.
So you could have a lookup table, right? But then now you have some manual configuration that has to go on. Or you have to have like smart layer 3 switches that have to figure out where things are, right? So we have dumb switches because we're cheap. And we bought the cheap Amazon switches, the TrendNet or whatever switch that you buy on Amazon for like 20 bucks right there. It just switches stuff. It doesn't do anything important, right? And so what the host needs to do is it says, hey, I'm going to send to 192.168.0.200. The host needs to ask, who has that IP? I can only communicate on the data link layer, right? I want to communicate at the network layer, so you simply ask the network in a broadcast message, who has this IP address? And the owner of that IP address responds, I have it. And then once you respond that you have it, now you can communicate over, and when I say I, right, the I that's responding is the data link layer. So the data link layer, in this case, let's just say it's Ethernet, but it really doesn't matter. Ethernet says I have 1, 2, 3, 4, 5, 6. That's me. I have that IP address. And now this host over here learns that its destination's data link layer address, and it can now communicate at the data link layer. So the next question becomes, is that's all local to network, so you talking to your printer, what if you want to talk to Google? You can't ask locally who has whatever Google's address is 64 or something. So you can't ask that because that's not local, right? So if you say you're going to go, let's just say that it's 64s is Google. So 64s, you're going to communicate at the IP address, but your local network can't do that. What happens?
Send it to the router.
You send it to the router. So the router has a table. It says, if everything goes here, 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 right? Your home router probably has 1, and that's whoever your ISP is, right? So you go down and you say, who has 64, 64, 64, 64, right? Well, that is not a local address. Your host knows that because it knows what its own address is. In DHCP, we also send back the network addressing and the default router and all that other stuff, usually. And so it's not local. So it sends that packet to the router. Now, in the rare case these days, if your DHCP server is not also your router, you would have to ask whatever your IP address, who has this, right? And your router would respond with its Ethernet address. And then you would send that packet to the router. What happens at the router? Right? So the router, you arrive with this packet over here, right, at the physical layer. So it has a data link layer, network layer, and let's say that you've got lots of money and you have public IP addresses, so we're not dealing with that yet. Again, right? So we can strip it off right here and just replace the data link layer. Because your router is going to go out cable modem, Comcast, whatever. So we're going to strip off the data link layer and we're going to replace it, but how do we find what to replace it with? What's this supposed to be?
The next hop.
It's the next router, right? So this router also has a table inside it, just like your host adapter, of what its router is. It has a table, and that next hop would say, okay, 64s goes out port 4 if the router just came on, which is unlikely, but if it did, it would say, who has your next hop, let's say is like 128 all the way across, right? It would ask who has 128, and then it would get a data link layer address, right? And now it would know that port 4, which is where this is going to go out to, is at this MAC address, and it would strip off the data link layer and replace that data link layer again. And it would go on and on and on and on until it reaches its destination. And at its destination, everything happens just like it was local at the data link layer. Now there are some funky things that can happen with layer 3 switches where not everybody is asked, right? Because you can configure so that it doesn't broadcast out everywhere. And then you have some crazy things like you might have some circuit switching inside of there with point-to-point protocol, right? But it all still works the same. You have an IP address. If you don't know whose IP address that is, and when I say that's the data link layer, you don't know the match to the data link layer, then you ask via ARP, which is what we're talking about, who has that? And then it gets back and you replace that part of the link and it just goes through the internet. So now we have fixed everything except for one thing to actually move packets, right? From an implementation standpoint, while it would take a really long time, you could actually implement, you have all the knowledge necessary to implement this. With the exception is when we're doing this, right, this right here is always the same. The problem is that it's not always the same. So the physical layer, because of different specs and different implementations and different medium, right, the packets aren't always the same size. So we run into yet another problem. Our last problem is, let's say this is Wi-Fi and this is Ethernet, right? And then maybe like point-to-point or something down here. Well, Wi-Fi has a packet size of 2.3K. Ethernet has a packet size, if the jumbo packets aren't turned on, of 1.5K. Point-to-point has a packet size of 900 bytes. So what do we do then?
You have to break the packets apart.
We have to break the packets apart. So, and that's what was done early in the internetworking. So we put the burden of the breaking the packet apart on the router, right? And so every time the packet gets smaller, it has to break it. What else could we do? We could also probe the network to find out what's the smallest packet, and then just send that packet. So let's examine both of them. So there's some trade-offs. So think about this. All right, so this is Wi-Fi. This is Ethernet. Typical access point, right? Wi-Fi goes to Ethernet. Every access point ever, right? Except for your cable modem, it's all built in. But Wi-Fi to Ethernet. So this is 2.3K. This is 1.5K. What do we do? We break it up, but how do we reassemble it, and where do we reassemble it?
Doesn't Wi-Fi have a fragmentation?
Huh?
Doesn't Wi-Fi have a fragmentation set?
Yeah, well, we'll talk about that though.
Okay.
Right, let's say that your access point receives an actual 2.5 or 2.3K packet, right? And it needs to send it over Ethernet at 1.5K. So the first option is let's break it up. Well, when we break it up, what do we mean? So we have this packet that looks like this, and this is the data link layer, right? This is the network layer. This is data, which is condensed because it's way, way actually bigger. And then this is the footer for the data link layer, most of the time. So what do we do? And where are we breaking it up? Well, we're not actually breaking up the data link layer, right? Because we're stripped that off. Because it's necessarily in a router moving from one data link layer to the other. So we've stripped that off. But this is still too big. The network layer and the network header and the data is still too big. So what we do is we duplicate the network layer somewhat, right? And then we put a data packet. And then we duplicate the network layer somewhat, and we put a smaller data packet so that they equal each other. Worse, better. Okay. But we can't just duplicate the network layer. Why? If we took the network header, in this case IP, and just duplicated, what would happen?
Checksums.
Checksums would be wrong, right? What else? And ironically, we are gonna duplicate the checksum, but there's other things that would be wrong. So the biggest problem is if we just duplicate it, right, inside of here we have a sequence number. Do we remember sequence numbers from like almost 3 weeks ago now? If two packets arrive with the same sequence number, ironically we're still going to duplicate that, but when we were talking earlier, if two packets arrive with a sequence number, what happens?
Disregard.
We drop the packet, right? It is a duplicate packet. Ironically, we are going to duplicate the sequence number. But what we are going to change is a couple things inside of here, right? So first, there's a flag called more fragments, right? There is also inside of the IP header, if you remember when we drove it up, is something called an offset. We're going to change those. So we're going to duplicate most of the IP header, including the sequence number, but we're going to change the offset from a whole packet would have offset of 0, right? A sub packet may or may not have an offset of 0. And then we're going to change this flag. So in this one, which one do we change? So actually, in this first packet, so this was our original, it was too big, and so we divided it into two, right? We set the more fragments to 1. So while this entire sequence is still the same, or this entire network layers header is still the same, we change only the flag to 1. The offset is still 0 because it's the first, right? In here, we set this to back to 0, but we change, in this case, if we went from 2.3K to 1.5K, we change the offset to 1500. And everything else remains the same, including the total length, including the checksum, including the sequence number. Why does that work?
You combine the data before you use the checksum.
Correct. Right? So right here, when we're looking, right as we enter the network stack at our destination, if this is our destination and we're crawling up the stack, right? The first thing we check is this a duplicate sequence number? And, right, logical and, is MF equal to 0? If it is, then it is a duplicate packet. If it is not, it is a fragmented packet. And then it goes off to a separate subroutine to put those packets together before it's passed back up to the transport layer. The problem is we ask the router here to fragment the packet. So let's say this is going through the internet, right? So the length of this thing is now 1500, right? And the length of this thing is 800. Let's say that it's going through the internet and it reaches point-to-point protocol. Point-to-point protocol has a MTU of 900, right? So what do? Well, we have to, this one actually fits, right? But this one has to be broken up. So now this one gets broken up to 900. And then we have a 600. And then we have an 800 under here. What if you hit something that has something small? Right? You can see that we're going to start having bandwidth misuse as we go through the internet. Now there isn't all that many MTUs, right? Because there's simply not a giant number of active data link protocols, right? But there are a few, right? So in reality, getting past your cable modem is probably going to be the smallest because cable modems use a packet size of 800. This also has, but when you're doing this, right, you still get to send at 2.3K. And then the host, you can't have the routers rebuild all the packets in between because you're already messing with them on putting load on them by fragmenting packets, right? So all of these packets arrive at the host, are reassembled, and then passed to the regular part of the network stack, in this case IP, and then processed as normal after they're reassembled. So what are some of the pitfalls? So in this case right here, where now we have 3 packets, right? They all have the same checksum. There is no provision to retransmit a fragment of a packet. So the probability of packet loss after this is now 3 times what it was, because we have 3 separate packets, and if any one of those is lost, all of them have to be retransmitted. See, now in this case, what we're talking about here, the host has 0 idea that it got fragmented, right? It is still sending 2.3K packets because it has no idea that they got fragmented. So we've increased the probability of loss, right? We've lost some bandwidth utilization at the end of the network, presumably where people really care. Anything else? What happens if we lose one of these things?
Is there no real way to tell besides checksum?
Yeah, so normally, like if we lose a packet, right, we, in the IP stack, if you lose a packet, timeout happens, we talked about this, right, and then you don't, the host doesn't receive an ACK, and so it retransmits, right? So now you have basically a bunch of queuing that's happening over at the host, where not only do you have a queue for regular like transport, and you'll see when we get to the transport layer, we're going to use that ACK thing a lot. But so now you have not only queuing for the transport layer, but you're also queuing for this fragmented packets. Right, and so there's a lot more memory use on the destination end because we're just waiting. How long do you keep those things? Right? Do you keep it a timeout? right? What happens if it arrives late? And then you'll see what happens when we start in TCP, when we start sending packets before the timeout. So all that sorts of things. So it would be better, and network experience has taught us this, it would be better if we could just send the smallest packet necessary to get through the network. Or I guess the largest minimum size, right? Find the minimum size in the whole network and send that packet. Or I guess find the maximum size in the network and send that packet. So in this case, it would be nice if we just sent this 800.
Does anything actually do that in the real world?
Oh, it does do that. In fact, all modern computers do that.
Huh.
So the question is, how do we do that? How do we do that? So, we're going to go from Wi-Fi, which is 2.3K, to Ethernet, which is 1.5K, to point-to-point protocol, which is 900 bytes. And we want to find somewhere in that 900 might be 10 hops deep, right? We want to find somewhere in the network what is the lowest, what is the largest, lowest number. We want to find that 900. How do we do that? There's another flag inside of IP called the DF flag that is the don't fragment. So MF was more fragments, DF is don't fragment. It means if you receive this packet, don't fragment it, right? So we send out our big packet, and it has all the layers in it, right? But DF is set to 1, right? What happens when we reach this router here? It drops it. It does. So we kill this packet, but it doesn't just drop it. It sends back an ICMP message. We'll talk about ICMP also, but it sends back an ICMP message, which is basically an error message saying, basically, try 1.5K. The host receives that. So what does the host do? It sends out now a 1.5K packet. It makes it through this router and then arrives at this router. This router will drop it, right, and send back an ICMP message that says try 900. And this will continue on until you make it through to your destination and you get no more ICMP messages. And you start getting ACKs. So now we found it, right? Any problems?
You don't store this at all, so you have to do this every time, just send one, correct?
Well, the host knows though, right? So the host can now just start sending, the host can store it and say, I'm sending 900
Okay, so
packets.
the host does store it.
Yeah,
Okay.
host is sending, I'm sending 900 packets. What happens?
The receiver would have to do the same?
Yes, the receiver would have to do the same, right? And the receiver actually is going to do the same. Though you might be able to figure out if you're receiving 900 packets, you should probably send them, right? So there might be some implementation jump arounds, right? There's some other problems though, right? Routes in the internet are dynamic. You don't always get the same route, right? So getting smaller is actually not a problem because the don't fragment flag is still set, right? So if getting smaller, it happens to happen, then you'll get an ICMP message back with 800, try 800 or something. Getting larger is a problem, right? Because larger pipes will let's say that your route no longer goes through this 900 and is going 1.5K the whole way, right? How do you find out that you could do 1.5K and you're not using it? And the answer is you simply try occasionally. So, and that would be up to the implementation for whoever's writing the network stack. So by I almost guarantee you Windows is different than Linux, is different than AIX, is different than whatever, right? It's an implementation. Every once in a while, and you technically don't ever have to try, right? You could just say, for this entire communication, I'm always going to send 900s, unless something comes back smaller, and then you just live with it, right? But you might, to get bandwidth increases, try occasionally to do something bigger, right? And fail probably, because it's probably still the same path, but you would find out. Is there any other problems with this?
There are multiple paths, or there might be multiple paths.
There might be multiple paths, right? And so now you're going to pick the smallest of those multiple paths, right? Because you're not trying to build a picture. When you're sending these packets, you're not trying to build a picture of the internet, right? So some of the problems is that most of the time it might go over 1.5K, and then sometimes it goes over 900, and so now you're always using 900. There's another actual problem with this. So, and this is a really good example of it. This is 900, right? 900 is the packet size for point-to-point protocol over MTLS. So MTLS are these ridiculously high bandwidth pipes in the middle of the internet. So let's say that this is let's say it's a 100 gig pipe. You have a 100 gig pipe, right? This is an over-exaggeration because the way that this actually works is it splits up packets and all sorts of other things. But these are the things you got to think through, right? So MTLS is running 100 gig, but it's only at 900 byte packets. Let's say you have a lot of money and you buy yourself a gig pipe to the internet. And your next hop is MTLS. Right? And your packet, to get your one gig pipe to the internet, you have to use jumbo packets of 9,000 bytes. So you technically have a 1 gig pipe over jumbo packets to the internet. Right? What happens when you get here?
It tells you that I can't take that.
So, but this could do 100 gigs. It really doesn't matter that it can do 100 gigs. It doesn't matter because the packet size is 1/10 the size, right? So essentially, while you have a 100 gig or 1 gig pipe to the internet, you can only ever practically send 100 megs. For a communication because of packets. Now, it's a gig, so you can send 100 megs at a time, which would be fine because it would, but it'll also recognize because realistically, you're only ever going to get this because to get 1 gig, you need those jumbo packets. And now you're sending short packets, right, which are not utilizing, if you remember back to the data link layer, you're no longer utilizing your network efficiently. Your packets are too short. And you have these open spots in the bandwidth because your packets are too short. Now, in reality, MTLS actually takes large packets and splits them up over different pipes, and then puts them back together so that you don't, we use this 900 example because it's actually MTLS, but MTLS is the rare case where it actually puts the packets together at the end. The router itself does. But you can run in architecting, you can run into these problems. You're like, well, I have 1 gig Ethernet. Even in local Ethernet, you're like, I have 1 gig Ethernet. And you're like, okay, that's great. you know, do you have jumbo packets turned on? All your switches support jumbo packets, right? Can you actually utilize that? Or are your packets too small? Or 10 gig or 40 gig, whatever you pick, you'll run into all these problems. So ARP and DHCP and what we're about to talk to, which is ICMP, all sit on top of IP. So while they are integral, like IP wouldn't work without these things, technically they're implemented as a transport layer protocol. Or actually they're technically implemented as an application on top of UDP, which we will eventually get to transports, right? So you'll find that UDP is basically just IP with almost nothing else. And then the application that sits on top of that. So we've been putting like data packet for DHCP and data packet for ARP that's carrying all that data, but it's technically an application, right? And so it has a protocol also. Just another header layer to be stuck in here. So how these errors are transmitted across the internet or local network or whatever for IP is a protocol called ICMP. It's Internet Control Message Protocol, right? It is how ping works. It is how trace route works. It is how don't fragment works. It allows us to send messages about the network to people that are to entities, in most cases this is machines, that need to know about it, right? So we have used ICMP already in the don't fragment flag, allowing us to say, hey, when I say try 900, that's ICMP that's saying that. It also allows us to do things like traceroute. Traceroute works by setting the time to live field, which really isn't a time, it's a hop to live. And because each time that an IP goes through a router, that is decremented. So you usually set it at, I think it's usually set at 64, and it's decremented as it goes through all the hops. And that's super important because it is entirely possible to have misconfigurations in the network and you have packets that live on forever inside of the network, consuming bandwidth, doing nothing because of a misconfiguration. And you want those packets to die, right? So we put a time to live field inside of the IP header to do that, which again is time to hop. And then you can set that because ICMP is an application layer protocol. You can use ICMP to send things through the internet to learn about the network, right? One of those is ping. It's an ICMP message that hosts are supposed to, not in the age of security, a lot of them don't, but are supposed to respond to, say, hey, this is me. And they'll also use it by setting the time to live field. You can see exactly how many hops you went through to get there and what hops those were. And you can also, ping also allows you to mess with the don't fragment flag and set the message size. So you could actually see, hey, is jumbo packets turned on in my network? Ping will actually allow you to do that. Hey, I bought this cheap Amazon router, does this support, or Amazon switch, does this support jumbo packets? Well, you can just use ping to find that out. Ping across that switch and set the size to 9001 and turn on the don't fragment flag, and it will tell you. So what are some of the errors that we might run into? We've said a couple of them. We're gonna have ICMP. What things would we need to know?
Most of the address doesn't exist.
A destination unreachable, right? Address may exist, it just might be the network's misconfigured, right? And so destination unreachable, right? So that is definitely one of them. What else? We said another one, right? Don't fragment. What else? Just talked about one. So what happens when a packet dies because of time to live? We get an ICMP message back. The time exceeded. And there's one more, which I talked about also. It's a reply request, right? A ping. Those are all of them. That is all the tools you have to work with in ICMP. So you can have destination unreachable, right? You can have time expired, you can have fragment, and you can have echo request, right? And that is it. And the question is, how do we actually use that functionality to our advantage? How would you go about with that's the only messages that you have, right? And you're, let's just say that you're a newly assigned administrator, or you just broke into a network and you want to find out what all is on the network. What do you do?
Ping sweep?
Huh?
Ping sweep?
First thing we do is a ping sweep. It's not a guaranteed method because some things don't reply to echoes like they're supposed to, right? So we could do a ping sweep. Could we find out how many routers are in this network to get from one to the other? How many layer 3 switches are in there? Sure, we could do that. We can use traceroute to find that out. It would take a while, but so you do a ping sweep, you find out who all responds, right? And then you start trace routing each of those to try to map out the network. Can't find out layer 2 switches, but you can find out layer 3, right? What about you want to find the maximum packet size from one place to the other? How do you do that?
The way you just said it.
Yeah, you can use ping again, and ping has a switch to set the don't fragment flag, and then just set the size you want to test. So usually you test known boundaries. So you would test highest to lowest first, right? So jumbo packets for Ethernet, 9,000. So try to send one that's 8,999, right? See if that makes it. If that one makes it, everything else is going to make it, right? If that doesn't make it, then you try the next boundary, 2.3K. Try the next boundary, 1.5K. Try the next boundary, 900 bytes. Try the next boundary, 800 bytes. And find your way through. Any other stuff that we could do with ICMP?
Ping of death.
We could do the P and death. So what could we do more exotically in all the stuff that we've learned so far in the class? More exotically, what could we do to find out stuff? Let's say the network guys were really, really paranoid about ICMP, so they turned it off in their whole network. Don't know how they're going to manage their network very well now, but they turned it all off. Right? Is there a way you can find out computers still? The answer is yes. Right? Why don't we send the first packet for a TCP handshake? right? And then test all the well-known ports, looking for a TCP connection, see if they respond. Not that we're gonna do one for reals, but see if they respond, and then you'll find, and it's essentially ping again. And if you're in control of the tool, you're down where you're writing at the data link layer, you can do everything you did with ping again at the TCP layer for other ports. So we now have enough information to be able to not only send an IP address packet across a data link layer network, where data link layer doesn't communicate an IP at all, right? But we can also transit to other networks. We can also have maximum transmission unit sizes, MTU sizes of whatever, right? And we can either rely on the routers to fragment that, or set the don't fragment flag. Is there, from a security perspective, is there any advantages to letting your packets fragment? Or making your packets really, really small? The answer is yes, because like an IDS system will only look, in the early days of IDS systems, it would like save 20 packets and try to evaluate the flow. Well, what if you were sending 1 byte packets? Right now you only have 20 bytes, right? And so you could evade security devices. So now they look for really small packets, right? Which is also, but you can also use really small packets to overwhelm networks and do all sorts of things, right? Any questions on any of this? All right, but go ahead.
Are we going to do security on Wi-Fi at some point? Or?
Oh, we'll talk about it. So maybe we'll do that as a case example on what not to do. Because Wi-Fi is like the biggest example of what not to do with security. How many people have had the crypto class? Okay. So for those that were in, bear with me for those that already took the security class. So the problem with the early implementations of WEP in Wi-Fi was not necessarily the key length, though that was not great. It was also the fact that they reset the nonce at 0 every time. And so the nonce is basically a salt that you send in the clear that you encrypt a packet with also. Right? And so that allows you to never have to worry about somebody doing a replay attack. So WEP was a blatant example of a bunch of network guys writing their own encryption protocol. They just thought they were smart enough to do that, and it made it through the entire standards body, and nobody caught that at all. How long does it take to break a web password?
Hours to minutes.
Huh? It's really minutes. There's a bunch of shortcuts now. It used to be hours. And that's to break the password, not just to get the content. The content's actually faster, right? To break the password and actually get the password. And it's now minutes. I think somebody published one, I think it was 12 minutes to get a web password. And it doesn't, and because it's an encryption problem, not a password problem. You can because if you remember back to web passwords, they were this crazy amount of hexadecimal digits, blah, 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 right? So the password was clearly random. And it was pretty long. It was 40 bytes long. But yeah, no, it was actually the encryption algorithm. But we'll use that as a case example as we get through the class on what not to do. If you're ever finding yourself writing an encryption algorithm, you're probably in the wrong. If you're writing the encryption algorithm and you're looking up on Google how to do it, bad idea. And that's basically what was happening with Wi-Fi. Any other questions? All right.